Today we are going to talk about iOS second advanced penetration testing and forensic techniques. My name is Omer. Let me briefly introduce myself before starting. My name is Omer. On the left-hand side, I'm currently employed with KPN, as known as Royal Dutch Telecom. And I used to work for companies like Verizon, IBM, iOS. My colleague, Mark, couldn't make it here. But if you ever happen to be in Amsterdam, come visit us and have a beer on us. The outline. We are going to cover basically the advanced techniques on iOS application reverse engineering, particularly dealing with 64-bit application, static and dynamic analysis, and hunting for the RSA keys and cryptography on this platform. And also a bit of penetration testing automation techniques and communication interception. How many of you have already done some penetration testing on mobile environments? Could you raise your hands? A few of them. And how many of you have already done some reverse engineering or penetration testing specifically on iOS environment? No one? One. Okay. Don't worry, we will cover everything, so you will have some clue to catch up with. Motivations. What inspires us to prepare a presentation on this and research is mostly we do a lot of penetration testings on the mobile environments. So we want to automate it and analyze it because the mobile environment and the applications are evolving, being part of day-to-day our life, day by day. And especially recent disclosures on especially the Snowden leaks related to the surveillance implants shifted our focus on the mobile devices. As you may see, heard, the German Chancellor, Angela Merkel, was being intercepted her calls and listened by some governments. And the iOS rootkits are not only a theory anymore, and it's practical. It's being sold, exchanged by the underground of the internet. It became a service. And reverse engineering our ARM environment are really fun. And we are going to see it all together. iOS security architecture look like this. We can analyze two major components. One is the user space. The second one is the kernel space. The user part consists of application sandbox, user partition, operating system partition, and all within the encrypted file system. And the kernel part consists of the security enclave and security elements. If we break down all the components, encryption and data protection is aimed to provide mobile users to protect their data from stolen attempts, and without modifying it, make it secure. The major component of the iOS environment security is being provided by the Secure Enclave. Secure Enclave is introduced iOS devices after Apple A7 processor, and later on. Security Enclave is simply a coprocessor which consists of encrypted memory and hardware encryption automated, simply pseudo number. If you ever dealt with cryptography, pseudo number is one of the major components of the cryptography that makes it reliable and strong. And there are also keybags that can be analyzed in two groups, system keybags and the external keybags where you keep encrypted device keys for the local device, and the one external is being used simply iTunes backups where the encryption key are being stored. The Make security framework simply is built upon the trusted BSD framework. It was first used in FreeBSD systems. It simply looks like this. It provides 4 different interfaces for secure system communication, and it defines the virtual file system, process signals, socket inter-process communication, and the pipe inter-process communication. And key policy interface provides a framework for module debugging, tracing, and detraces to allow developers to instrument and analyze their applications. Just to break down it to the more basics. When you have, as a mobile developer, once you develop your application and put it into the device, and when you start to run your application, it simply creates a process. And once it is run, it invokes the sandbox unit system call. This system call uses dynamic library to check specific policies, and these policies transfer to the sandbox kernel extension, and then it checks specific policy profiles, and then it installs specific policy profile to your application and sends it back to that signal, whether it is installed properly or not. This simply defines what you can achieve within the mobile application and what you are allowed to do, what you are not. If you want to look on a very abstract perspective, it looks like this. You create a process to make syscall to the make callout. Make layer checks whether a policy applied or not. And the simply sandbox kernel extension is just making a regular expression to check whether your policy is matching a profile, which is already defined in the iOS framework. So, on the left-hand side, we have profiles, documented profiles. Like your application could have has no right to do connect internet, no perform network operations, or right to the directory or the specific directories. But there are also some profiles undocumented. So reverse engineers found these profiles by reverse engineering. From a malicious application developer or security researcher, it could be interesting for you. For example, these profiles, mobile Safari, mobile mail, APSD, especially the sandbox compiler D profile. You can perform a lot of actions within the phone. For example, you can access to the log directories, recent locations, uh, temporary directories, log directories, and etc. And as sandbox profile usage is look like this. You simply invoke the sandbox unit with a profile given as an argument to the call. And file encryption under the iOS system is looking like this. You have a hardware key coming from the security enclave and the passkey. Once you have an iOS device and define your passkey, these are combined and conveyed to the class key. And we have each encryption file metadata for each key, and it is encrypted. And file encryption also defines API classes to define specific actions on the file operation within the iOS environment. For example, file protection, we can set a file without any protection. The protection could be complete unless open. And these API classes also define some attributes, like when the attributes are working like this. For example, when you want to allow to write to a file, you can define as this operation could be done after once the device are opened, or you can simply allow a file can be written always or read always. And this call can be achieved either an NSData call or the NS file manager. The subtle difference between two calls is by using file manager over NSData, the reason behind is you can specify these attributes, but NSData doesn't give such option to the developer. As I mentioned, the keyback locations, the Xsl internal locations are stored on your device. This directory, private lockdown directory within your phone. And there are also external iTunes backup location that contains your, for instance, Mac device, and it contains all the encryption keys. And there are open source decryptors and commercial solutions where you can perform cryptography attacks, and you can try to find out the key. But it is being improved, and there are some changes take place after iOS 8 and newer versions of the implementations. Macro file structure has been changed a little bit on the 4-bit implementation. Macro is simply executable on the iOS devices. And it looks like this. The macOS 64-bit implementation built upon the 32-bit. However, the segments little bit changed. For instance, the structure called segment command 64 defines the VMware structures where you can define some specific privileges, which part of the VMware VM memory can be read, can be not. From a security perspective, this is important because you would want to know which location is being used by a program. And for instance, encryption key be stored, what kind of action could be done. Because if a malicious application runs on the iOS device and the application uses wrong permissions on the segments, you can do malicious actions, and in other words, the sandbox mechanism couldn't be used in the proper way. All right, these were the most technical and useful theoretical information. I prepared the presentation as a hands-on challenge. You will be provided to all the executables after the talk. From GitHub, you can download and try. iOS binaries implements encryption ID to protect executables from piracy. So the consistency, integrity checked by the encryption. So it is a section in the executable. When we used to deal with the 32-bit applications on the iOS environment, we simply use object tool and then find the encryption section. If the encrypt ID section is returned false, it means the binary is encrypted. So in the past, we used to find out the encryption section and VM address, the virtual memory address, and to find the length of it. And we simply run the executable under a debugger, define the sections, dump the binary, and we can simply extract unencrypted executable. The game is pretty much similar on the 64-bit environment. The only subtle difference is we need to use Lldb Debugger. It's a new debugger, uses the CLang keywords and syntax, and it comes with the default compiler within Xcode framework. So how you can get this debugger running? Everything is stored under the Xcode default developer directory. So you can simply attach to the HDI util and define the specific images that you are dealing with. For instance, I was dealing with the 8.7.1 implementation. So it contains all the helpers and the utilities under the specific directory of the device support. Like the most important one is you will need Debug Server. To be able to run Debug Server on your iOS device, we need to set an entity file for the Debug Server. This is simply a sandbox policy file that you define what your executable can do on the device. Simply, if it can run, for example, process ID for each task, run unsigned code, and etc. So that's what we want, because we want to attach an executable to the debugger server on the device and do debugging operations. So there's a tool called CodeSign. You can define entitlements as an XML file and then sign the executable, and you can simply upload it to the jailbroken iOS device. And once you upload the executable, you want to create a TCP connection to the device and do debugging on your computer. So when you run Lldb Debugger, you can select the remote iOS version that you are specifically dealing with. If you write down platform select remote OS, it will show you all the supported versions of the iOS implementation. Up till now, while I was doing reverse engineering on the device, my environment supported up till version 8.1. However, I was dealing with an executable, 64-bit executable, which was created and developed for version 7.1. So you define your executable, find the process ID, and you remotely connect to the debug server. The IP address is 215 is my jailbroken device's IP address. My debug server is listening on that port 666. So I attached, connected, and I list out the threads. It seems like the application is being debugged, and attached to the debugger, it seems everything fine. And if you ever done malware analysis or reverse engineering, reversing the iOS application shouldn't be so much difficult, especially if you know there are packers for the x86 Windows malwares, like it applies a lot of obfuscation, encryption, stolen bytes, a lot of abstraction that you need to deal with. But it is not the case for the iOS applications. I grabbed the binary and downloaded back to my application, so I was using IDA. Since there is no obfuscation and etc. iOS environments, I can easily resolve the functions names correctly, and it seems all good. It correctly resolves the function names and the arguments declaration. So whenever I do reverse engineering and static analysis, I always look for the imports and the interesting function names. The application I was dealing was simply using a asymmetric cryptography to encrypt some interesting information, especially the network traffic. So I went through the interesting functions. As you can see, there are some interesting function names, such like their public key, RSA encrypt data. So it tells something about it. And you can look on the function definitions on the Apple developer forum and see how it is being used. So it was very interesting here that the application was evaluating function via this application was evaluating certificate via this function call in here. In here, the data being encrypted over here because I see file encrypted with public key. And the calling convention on Objective-C is a little bit different than C++. In C++, object pointer is followed by the function name and function parameters, and for the Objective-C, the parameters different as it comes after the column. And this function evaluates the certificate and makes me confident because these are the default function calls, as you may check on the Apple developer forum, the function prototypes. It gets the block size, public key name, and checks if the security trust and you can just call the cross references and see where these specific functions is being used. For the file encrypted, I use this specific constant, and this specific constant says like function certificate cannot be read. So this specific constant needs to be used somewhere that the function actually evaluates the function, and its specific location, I can simply use debugger to obtain either the private or public key, depending on their implementation. So when I jump to the cross references, it looks like it do memory allocation and then sets it to the 0 to allocate something and store. It makes me curious because that looks like when you want to read a certificate, these are the specific steps that you need to take. And just as a reference, LLDB commands pretty much similar to the GDB. We covered this. Okay, the encryption file. This is the location for encrypt file, and it is being called by the, probably the function is being storing the private or the public key. Reversing on iOS environment is looking like this. Observe the application, what it's doing, revoke encryption, and obtain flat binary, what needs to be taken out, and combine static and dynamic analysis. And now, once I obtained the location, IDs, and specific function names, what I need to do is just observe and analyze binary on the debugger. So I reattach my executable to the LLDB. So I can define the good thing about debugging and reverse engineering iOS environment is you can simply pass a breakpoint to the specific function name as it is shown on the very first screenshot, like file encrypted file. So put a breakpoint there, run the executable, and see what happens. And I run until the end of the function by stepping in, and then I dump memory with the LLDB command like memory read out file, take it to the flat file, and I opened, it was containing the certificate. It is a public certificate. However, when I was testing this application, the previous implementation was done a private key. But later on, they switched to the public key. It was a good thing and correct implementation. The application penetration testing on the mobile iOS applications look like this. These are the most common vulnerabilities and the groups of findings where you can relate. The most common issues are related to the weak server-side controls, insecure storage, like the information stored on your local device, which is supposed to be on, for example, keychain and etc. And people think like when they implement, programmers are always lazy, and they think like it's a mobile application, so you cannot do pretty much anything. So they rely on most of the time assumptions. So if you want to analyze in groups, we can divide into the subsections like application mapping, client attacks, network attacks, server attacks. It's pretty much similar to the mobile, web application assessment, but the only subtle difference is binary is being involved, and the platform mapping and data flow is different, and the APIs is being used is framework, part of the framework, and file system analysis needs to be involved to do testing. So network flow analysis can be achieved, for instance, forwarding your traffic to your device. Of course, you need a jailbroken device with syntax and dynamic port forwarding, so I can pass the data, my Wireshark. It's also interesting to have a packet analyzer. It's new, recently implemented Krakow packet analyzer, so you don't need to install a lot of packages to be able to run on Mac iOS environment. So it could be interesting because if you manage to obtain public or the private key that encrypts the communication, you can trivially decrypt your packages, for example, via the Wireshark, implementing a Lua script. Whenever it goes slow, you can easily decrypt the communication on the fly. But what if not? What if you cannot obtain encryption or encryption key at all? So this time the function hooking comes into play. Function hooking is a technique. It's simply you are using the function, you are calling your function a function created by you, obtain the information passed by the function, and then let go the function supposed to work as it is. And iOS SDK defines SSL implementation as it follows. SSL context needs to be defined, and the data passed as a pointer, data length, and size to be processed. And in a similar manner, SSL write operation is defined as well. You have data length, and the process ID. The data to be processed, simply length. And you can check out the details on the developer center. Important thing and the most interesting part is you can implement a function hook. So these are the read and the write calls to be forwarded to your own function and obtain the content and let the application work as it is supposed to be, the way it's supposed to be. So we implemented a sample hook. The source code will be published on GitHub, so you can take a look on it. It's simply a dynamic library. So you can invoke dynamic library while executing an executable, and it will intercept via the function calls as defined. So you can obtain the SSL context. So once we implemented this, we came with an interesting analogy, top-down hook style. So we intercept every function, keeps a copy for us, content for herself, as a similar manner NSA does. So once you run the application dynamic library in the manner, it looks like this. You can obtain everything in the plain text. So the point we want to draw is that rootkits on the iOS environment is not a conspiracy theory anymore. If you take a look on Dropout.G project, it's one of the Snowden leaks. It's simply a software implant, and it stores information and passes to the NSA for storing. And this is the sample code maybe you have seen on internet. It is iPhone rootkit book. So it simply shows and implements the sample hooking, for example, the microphone listening. So you can implement a code that records while you are talking to someone else on your phone. As a penetration tester, you did binary analysis. You would want to do some automation, day-to-day tasks to be able to accomplish some actions that you don't want to do by hand all the time, and make some gain some free time on analyzing the interesting things. So while doing application level analysis, we really love to use burp extensions. We extend the framework by writing Python or Java code. And there are third-party interesting extensions that you can use. These are the most common extension classes that you can use to extend the framework, burp framework, like to retrieve cookies, extended callbacks to register actions, and scanner intersection points. Burp Pro provides scanner. Just simply send automated payloads and return back, so you can define on insertion points to automate application level analysis. And these are some common extensions that you can use. For example, interesting one could be active scan, where you can passively do scanning and path injection. And it can also be interesting if you are using Web Inspect scanner, so you can share the results between burp and Web Inspect. Additional scanner is looking like this. You can define specific actions, for example, content sniffing, client size, XSS injection, and etc. Like comparing different return values, whether there can be a potential privilege escalation or not. And burp extension, one of the interesting one is where you can do dictionary generation and do automation based on, for example, username and password brute forcing. And one of my favorite one is Xsl Validator Plugin, where you run a JavaScript running on a server. It simply sends your payload to the server, and you run it the extension generated validator payload path. So it will able to validate whether application is vulnerable by simply matching a regular expression, the keyword you define, via function evaluation. So if the JavaScript is being evaluated on the insertion points, the application you are testing, that means we can automate testing without dealing the manual analysis. So this is a sample test where you define the payloads and it is run to the server, and we are checking whether these being match the regular expression we defined on the square. And that's it. Thank you very much. Do you have any questions? Yeah.
Hi, you mentioned OWASP Top 10, mobile OWASP Top 10, but when it comes to designing an application, it's, well, I assume that it's better to use application verification standard, also made by OWASP. But do you have any suggestions about more detailed checklist for developers for iOS applications?
Well, iOS Developer Forum has already defined some practical standards that you can apply while designing your cryptography, web application exchange, and etc. OWASP is simply a standardization of the common found vulnerabilities. I would definitely recommend checking on Apple Development Forum. Any other questions? I guess no. So thank you very much.